In this section, we're just going to review what you have seen in multiple courses about lines and linear functions. The reason we keep hitting you with the same material is that we build calculus up from just your basic formula for the slope of a line. When we start in on chapter 2, you'll see that that's basically where I start. And then we'll use infinitely many lines to estimate what's going on with a function. That being the case, we want to have this pretty fresh in your memory. So you've seen the formula for slope plenty of times, and then the point slope form of a line. These are your two most important pieces. If you look at point slope form, it's just the formula for slope. If you brought the x minus x1 over, you'd have m equals y minus y1 over x minus x1. It's just without the 2's. So everything comes from this formula for slope, and you'll see that we build an entire subject from that. I included some of the other basic features. Parallel lines have the same slope. Perpendicular lines, the slopes are opposite reciprocals. Vertical lines, your variable's x, horizontal, your variable's y, and they're constant in each case. And then your slope-intercept form, which is probably your most familiar form for a line, but the point-slope form is the most useful. So in this section, I just want to run through kind of the types of problems that you've come across, just really get this stuff fresh again. So in this first example, we want to build formulas for the equation of the line from a graph. Whenever you have a graph, it's helpful to think of slope-intercept form, y equals mx plus b. We know that b is our y-intercept. So in this one, that's going to be 2. So that's our y-intercept. And then if I can come up with slope, then we're in good shape to get the equation of the line. So we've got one point. We just need directions to another point. We could go up here. Let's go to this point here. So to get from this point to this one, we would go up 3 and then to the right 1. And then remember, slope is rise over run, so that would be a rise of 3, a run of 1, and so your slope is just 3. And so y would equal 3x plus 2. So that would be your equation. On this one over here, your y-intercept is -1. And then we need to find another point on this grid, so we could use, you could use anything. I would pick out one of the points that makes it pretty obvious that we're crossing through the grid here. So to get from our y-intercept to this point, we would go down 1, so a negative rise, and then we would run to the right 3 units. Always move to the right. Go up or down with the y values, but always move to the right. That's the way we orient things here. So your slope will be -1, a fall of 1 unit for each 3 units you run to the right. And so your equation then would just be -1/3 x minus 1. That's pretty much all there is to lines. You could flip this around. Given these two formulas, could you then graph the line? That's a little more direct. I prefer to build functions from graphs because in real-world type applications, you don't just look at something and a formula pops out, at least not all the time. And that being the case, you collect data and you try to fit curves or lines or parabolas or exponential functions to that data. So being able to come up with an equation from a graph is important. We have another form for the equation of a line that you've seen when you've solved systems. This is often referred to as standard form for the equation of a line. Both variables are on the left and the constants on the right. So in order to graph a line, we just need 2 points. You could solve for y here and then do what I had suggested in the previous example, or we can go off the x and y intercepts. So your x-intercept, you're setting y equal to 0. If you set y equal to 0, then the equation simplifies to 3x equals 6. So when you're in this form, you can almost, quickly eyeball what the x and y intercepts are. So this would give us x is 2. So your x-intercept then is 2, 0. 0 for y, x is 2. And your y-intercept, we would set x equal to 0. And again, the reason these are flipped, if you're a y-intercept, you're on the y-axis. What's common about every point on the y-axis is that x is 0. You haven't gone left or right. Same is true for the x-intercept, but with regards to the x-axis. So if x is 0, plugging that in, that would knock out the x term, and you would just have 2y equals 6, or y is 3. And so your y-intercept is 0, 3. And that makes it pretty easy to make a sketch. So call that 3, call that 2. We've got 2 points. You can read what your slope is off of this. It'd be negative 3 over 2. And there's, I missed. And I'll show you how you fix that. You just make that dot bigger. Now it goes through. So there's the equation of the line. You can see that your slope would be negative 3 over 2. And if we had written this in slope-intercept form, we would have subtracted the 3, divided the 2 there. And then also we divide the 2 into the 6, so we would get a 3 there. In general, I don't really care how you come up with the graph or the equation. They all come from just the formula for slope. But if it's in this form, it's really quicker to go after the x and y intercepts. All you have to do is really cover up each term and do a quick division. But just making sure that everything is linking together. That's it for these examples. Now we'll go into a little more details with the point slope formula in the next page.